Where are my slides? Believe it or not, we finished microprogram microarchitectures in one class last lecture. Everybody knows everything about them now? It's good. It's beautiful, isn't it? Yeah. We're going to talk about another concept that's beautiful, pipelining today. And hopefully we'll finish it today, including data dependence handling. You guys know about pipelining probably, right? How many of you know how it works? You don't cover it in 213?
How much is that chapter?
There's a chapter.
Chapter 4.
You don't. I know you don't design a pipeline processor. That's what you'll do here. But do you know about data dependencies, control dependencies? No? Some of you do. Who knows about data dependencies, control dependencies? Some. Who doesn't? Feel free to. OK, so most of you don't know then. OK, so this should be fun then. Well, even if you know it, it should be fun. It's fun for me after so many years. OK, so this is what I left you with, actually. Can we do better than a multi-cycle microprogram design? What limitations do you see with the multi-cycle design? And I think I've flashed the answer. What is the limitation? Yes?
You're only using most of the processor for one cycle out of many.
Mm-hmm. Basically, in a given cycle, you're using very, very little portion of the processor, right? Could say it that way. For example, if you're loading from memory, pretty much the entire data path is left idle, right? You're not doing anything at all in that data path. So you're wasting a lot of concurrency that you can potentially exploit. I already said this, basically. For example, fetch logic is idle when instructions being decoded or executed, right? Most of the data path is idle when a memory access is happening. I guess I could switch to the picture, but I'll show you the picture. That might be better. If you remember the state machine and the data path figure for LC3B, in certain states, you're not using, oh, there's the data path. In certain states, you're not using most of the data path. For example, I don't know if you guys can see this, but there's a state over here where we're waiting for memory. Remember state 33? Can you guys see it? But you can remember it, right? We were waiting for memory to return data. And conditionally, you go to state 35 or stay in state 33. During that state, if you look at this, this is the data path. Only this part of the entire system is being used. This entire data path is idle. You're not doing anything, basically. You're wasting all of these resources. So that's the downside of this. You built this hardware. You could potentially do more things concurrently, but you're not doing that. So the key question is, can we use the idle hardware to improve concurrency? And the answer is yes. And I'll show you with pipelining. Pipelining is a method to do that. So the goal is to get more concurrency, which is equivalent to throughput, basically more work completed in one cycle. And the idea is when an instruction is being executed or using some resources in its processing phase, process other instructions on the idle resources, potentially in different phases, right? And of course, on the idle resources that are not needed by that instruction. For example, when an instruction is being decoded, fetch the next instruction concurrently at the same time. When instruction is being executed, decode the next instruction. When an instruction is accessing the data memory, execute the next instruction. And when an instruction is writing its result into the register file, access data memory for the next instruction. So you can see that there's a pipeline now, right? Every processing phase is happening in the processor except for different instructions. And the hope is that these are happening in different resources such that they do not conflict with each other at all. Now you're processing 1, 2, 3, 4 instructions in parallel. One is being fetched, one is being decoded, one is being executed, one is accessing memory, and one is writing its results into the register file, which means that you're actually executing 5 instructions, right? Based on this. It's pretty powerful, right? As long as you have the resources that are separate to do that, it's great. And most of the resources are actually separate in this data path. Maybe fetch and memory access is not separate, right? They both need the memory. This is called a resource contention, so you may not be able to do this.
And the bus.
And the bus, exactly. So we'll actually try to increase the resources. So if you really want to do this perfectly, you need to increase the resources because one single bus may not work in this case. And we will see that pipelining actually increases area cost a little bit. And the goal is to improve concurrency. OK, so the basic idea is very simple, basically. So more systematically, pipeline the execution of multiple instructions. It's like assembly line processing of instructions. You know assembly line processing in a factory? When a part of the car is assembled, some other part is being built toward the end of the factory, right? And these parts basically move through the pipeline such that eventually they form the car. That's one example. I'll give you a laundry analogy, which is also interesting, I think. So the idea is divide the instruction processing cycle into distinct stages of processing. They don't necessarily have to be the 6 stages that we discussed. It could be 25 stages. And ensure that there are enough hardware resources to process one instruction in each stage. And process a different instruction in each stage. Make sense? Basically, if you are following the von Neumann model, which we have been following and we will follow for a while, instruction consecutive in program order are processed in consecutive cycles in the same stage, right? Hopefully, barring some dependencies that we will discuss soon. So the benefit is hopefully obvious, right? You've increased concurrency now. You've increased instruction processing throughput. So you're doing multiple instructions per cycle now, right? You're still finishing one instruction per cycle at the end of the pipeline, as we will see in the figures. But at any given point in time, you're doing multiple instructions per cycle. So hopefully, your throughput in the pipeline is one instruction per cycle at the end. But the latency of an instruction may be multiple cycles, right? So let me give you, well, I guess there's a downside to this also. And I've given you a part of the downside, right? We've discussed this. Resources may not be enough. So you may want to scrap the single bus design and have multiple buses to support whatever I described over here. And we will do that. That's one downside. But think about other potential downsides. Will this lengthen the time to process an instruction, for example? It may, and it will. Yes?
So when they talk about like cycle per instruction and instruction per cycle, so instruction per cycle, is that like how many things are pipelining at once? Or is that like just the inverse of CPI?
Yeah. So
they're two different things, right?
they're actually inverse of each other. Okay. So when we talk about cycles per instruction, let me, if you have a pipelined processor, I show pipelining this way. You actually always look at how many instructions you're finishing, completing per cycle. Basically, it's really instructions completed per cycle. That's not the same thing as how many instructions you're processing in a given cycle. Yeah. Does that make sense? Yes. And we will get back to this, especially when we talk about speculative execution. For example, you may be actually processing many, many more instructions than you need because you may want to achieve some speculative execution. You might want to do prefetching. But they don't contribute to instructions processed because they're not real instructions, right? OK? It's really the completed instructions. We'll get back to that. That's a good question, though. OK, start thinking about the downsides. We're going to try to get rid of the downsides later on. So OK, this is, well, this fits well. Basically, if you think about the execution of 4 independent add instructions, this is how I divided the pipeline, if you will. If you have a multi-cycle machine, assume that add goes through 4 cycles: fetch, decode, execute, and write back, write result. This is how 4 adds will execute, right? You don't fetch the second add until the first add completes. So every add takes exactly 4 cycles in this case. So it takes 16 cycles, or 4 cycles per instruction. Right? That's the CPI. If you look at the pipeline machine, this is what you would get, right? When you're fetching well, I guess let's look at this one. This is the first add. When you're writing its result, you're actually decoding the second add, right? And you're, well, it's actually this way, right? Where you fetch the first instruction, and while you're decoding it, you're fetching the next instruction, right? While you're executing the first instruction, you're decoding the second instruction, fetching the next instruction. While you're writing back the results of the first instruction, you're executing the second instruction, you're decoding the third instruction, you're fetching the fourth instruction. So at the steady state, if you will, steady state means pipeline is full. Here, the pipeline is not a steady state, right? Because if you look at this, this is time cycle 1, cycle 2, cycle 3, cycle 4. Pipeline is full when all of the stages have an instruction in it. here, if you look at it vertically, not all stages have an instruction because we have 4 stages: fetch, decode, execute, write back. At the steady state, if you will, you would be retiring or completing 4, you would be completing 4 instructions every 4 cycles, right? Which means you'll be completing 1 instruction per cycle, as you see over here. Make sense? So that's the throughput improvement. Now you have 1 instruction per cycle instead of 4 0.25 instructions per cycle. Right? You can think of it the other way around too. Okay, I'll ask this question. Is life always this beautiful? So what's the assumption here? Yes?
That you always know what instruction to run next.
That's right. That's one good assumption. What else? Yes?
The data is always ready when you need it.
That's right. Basically, these are 4 independent ads, right? Hopefully. They don't need the data from each other in this case. What else? Yeah?
Can you like physically or like you always feed those like hardware units in the chip? Like maybe like
Yeah, you may have some resource contention. Maybe in this 4 ads you don't have that, but you may have resource contention, as we will see later. Yes?
As always, that memory is not always 1 clock cycle, and it would be a bad design if you made your entire possible memory latency your critical path.
Exactly. Yes, exactly. Memory is another issue. How do you handle memory stalls here? And we'll get back to that. These are all good issues. So life is not always this beautiful. So we'll try to cover all of these non-beautiful cases and still try to get 1 cycle per instruction, or 1 instruction per cycle, and even more later on during the course. Okay, so there's this laundry analogy that one of the books has, the Patterson and Hennessy. Laundry analogy is a nice analogy, I guess, for this. Basically, 1 load of laundry goes through 4 different steps, instruction processing cycle, right? You place 1 dirty load of clothes in the washer. When the washer is finished, place the wet load in the dryer. When the dryer is finished, take out the dry load and fold. And when that's finished, ask your roommate to put the clothes away. Or do it yourself, right? You could actually ask someone else to do all of these, but I'm sure all of you have done laundry, right? It's every step is dependent on the previous step, right? But if you have multiple loads, they're independent, right? This is a multi-cycle laundry design, if you will. And different steps do not share the resources. You cannot dry clothes in a washer. You cannot, I guess, you don't need the dryer to fold the clothes, right? Nobody folds clothes in their dryer. Make sense? So it has these 3 properties. Steps to do a load are sequentially dependent. Different loads are independent. And different steps do not share resources. So it's kind of similar to instruction processing. Not exactly, but think about it now. So this is a multi-cycle design for laundry. It makes no sense, right? You'd be waiting. If you start at 6 p.m., you would be waiting until 2 a.m. to do 4 loads of laundry. If you have these resources, these 1 resources for each. Assuming that each resource takes 30 minutes to complete. Washer takes 30 minutes, dryer takes 30 minutes. So pipelining basically reduces that time and improves throughput, right? This is what you get to do 4 loads of laundry. You can do them in parallel. Basically, once the first load is in the dryer, the second load can go into the washer. Once the first load is being folded, the second load can go into the dryer, and the third load can go into the washer. And at the steady state, there is 1 load at each stage of the laundry processing pipeline, right? And you don't need any additional resources in this case, because it's beautiful. Everything is independent of each other. Each load is independent. And throughput is increased by 4 in this case, right? And you're done by 9:30 p.m. And then you can play games or do your 447 assignment. Actually, you should be doing your 447 assignment while all of this is going on. It doesn't matter. And latency per load is the same, though. If you look at this, latency is 4 time units, right, for each load. So that's critical. In a pipeline, you haven't changed the latency. Actually, we will see that you'll increase the latency, really, in a real instruction processing pipeline. But you improve the throughput. Make sense? By improving the throughput, you reduce the latency of the entire program or entire set of loads to finish, but not individual load latency. That doesn't reduce. Now there's another issue. You may have faced this. These dryers never finish in 30 minutes. If they finish in 30 minutes, you would be wearing wet clothes. That just doesn't work. So they actually look like this. They take longer than everything else, right? Is that everyone's experience? We need better dryers, perhaps. But if you increase the heat, then there's damage that happens to the clothes. So that's a trade-off, too. So let's assume the dryer takes 2 time units, or 1 hour instead of 30 minutes. This is what you get in a multi-cycle design. Well, you'd be up on, well beyond 3 a.m. And this is what you get in a pipeline design. Now your throughput is not 4 loads, right? 4 loads of laundry in parallel. Your throughput has reduced, right? The slowest stage actually decides your throughput because you cannot start the next load. You cannot put the next load in the dryer until this previous load is done in the dryer. Right? And this previous load is taking very long. Does that make sense? So this is bad. This means that you really want to balance the pipeline stages. This is one way of doing that. One way is actually compartmentalizing the dryer, but that doesn't work, right? Because it's really a latency problem. So how do you fix this problem?
Buy a second dryer.
Exactly. You can buy a second dryer and put the put the alternating loads in different dryers such that their latencies can now overlap. Right? So pipelining is really about overlapping latencies, improving concurrency. Right? You have the long latency of a single instruction. You're overlapping it with different instructions. Now you're back to the same throughput, except you increase your cost. This is a very nice analogy because that's exactly how things work in a real instruction processing pipeline, too. If your multiplier is taking very long, and if you cannot pipeline it somehow, in this case you cannot pipeline it, then better to have a second multiplier if you want to keep the throughput. And multipliers are a good fraction of your program. OK. So an ideal pipeline. This is actually close to an ideal pipeline, if you will. What do I mean by an ideal pipeline? In any pipeline, our goal is to increase throughput with little increase in cost. Cost is hardware cost in case of instruction processing. An ideal pipeline has 3 properties. You repeat identical operations on the pipeline. Basically, the same operation is repeated on a large number of different inputs. This is the computer science terminology, if you will. What do I mean by this? In a laundry pipeline, you have identical loads. Or loads do the same thing, right? They go through the same stages. Now think about instruction processing. This is not exactly true, right? You don't always do the same instruction. Operation, in this case, means instruction. You don't always execute the same instruction on the pipeline. They're very different. So that's going to cause some challenges. And operations are independent of each other. There's no dependency between repeated operations. In this case, the second load has no dependency on the first load, right? You can reorder them perfectly. That's not true of instructions also, right? At least many instructions. I shouldn't say most, because surprisingly, there's a lot of independence which we're going to exploit later on. And finally, an ideal pipeline, you can partition the sub-operations, or stages, if you will, uniformly or perfectly, such that they're exactly equal. You're not wasting any time in each stage. Processing can be evenly divided into uniform latency sub-operations that do not share resources. In this case, I've assumed that that's the case. This takes exactly 30 minutes. Well, this is the cooked up. Well, not necessarily cooked up. That's the real case. But let's go back to here. This takes exactly 30 minutes, exactly 30 minutes, exactly 30 minutes, exactly 30 minutes. If that's the case, it's an ideal pipeline, right? But we'll see that it's not easy to do that. Automobile assembly line could be close to ideal. Doing laundry could be close to ideal. Not necessarily, though. Think about it. How about the instruction processing cycle? I've already told you, right? It's actually tough to make it ideal. But we're going to overcome those non-ideal parts. So let me show you ideal pipelining from an instruction processing standpoint. This is what we would like to do. So for an instruction, we have, let's assume that we're going to process, it takes t picoseconds to do everything related to the instruction. Fetch, decode, execute, memory access, write back. And after that, you latch the result, and you go on to the next instruction. The throughput of this is, or bandwidth of this is, proportional to 1 over t, right, picoseconds. You're completing one instructions every t picoseconds. Let's assume that we want to pipeline this with 2 stages and improve throughput by twice. If you would like to do that, this is what we can try to do, basically. Have 2 stages. One takes t over 2 picoseconds. Let's say fetch, decode, execute. Latch the result. In the next stage, you can do memory access write back. T over 2 picoseconds, you would hope. If you could do that, you will double the throughput. It turns out it's tough to do that. And if you want to improve improve the throughput 3x compared to the baseline, this is what you would do. Divide each stage equally, such that it takes t over 3 picoseconds, and you latch the result after every stage. Make sense? This improves your throughput 3 over t. This is kind of ideal. Well, there's overhead, as you can see here, right? Obviously, this doesn't come free, this latch. It takes time to latch things. And it takes cost to latch things. So let's examine it with that time. So if you have a non-pipelined version with delay t for an entire instruction processing, let's say, your real bandwidth, your real throughput is really 1 divided by t plus s, where s is the latch delay. Right? That's a simplified form. And if you want to divide it into k stages, you can divide, assuming you can divide this equally, your processing is really, each stage takes t over k picoseconds, assuming you can divide equally. That's an assumption too. But you also have this latching overhead, s picoseconds to latch at the end of each stage. Does that make sense? So your real throughput of a k-stage pipeline is 1 divided by t over k plus s. And assuming that you have your maximum throughput could be, assuming k goes to infinity, infinite number of stages, right? Your maximum throughput is limited by this latching overhead, right? So you can never get infinite throughput. This again Amdahl's law, right? If this latching overhead is really high compared to your pipeline stage, then at some point you don't want to keep pipelining because you're limited by that overhead. Make sense? Remember the Amdahl's law that I discussed earlier? This is another place where Amdahl's law dictates your maximum throughput, maximum performance. Okay, let's analyze the cost. Again, in a more realistic pipeline, cost, whenever you add a pipeline stage, you actually add latching cost. And we'll see that you can add other costs also if you want to keep the throughput. You may have G gates to implement everything to process every instruction. And the cost of a non-pipeline version is G plus L, where L is the latch cost. Once you pipeline it, even if you can divide gates ideally this way, G divided by K for a K-stage pipeline, the entire cost is you keep the same combinational number of gates, but now your latching overhead increases. Right? For each stage, you need to add 1 latch at the end. So it's LK. That's another reason why you don't want to pipeline more and more. OK. This is theoretical right now. Let's go into the details of it, to pipeline the instruction processing. Any questions so far? OK. So how do we actually pipeline the processing of this instruction processing cycle? You already know this by now, so I'm not going to go over it. Fetch, decode, evaluate address, fetch operands, execute, store result. You don't need to have stages that correspond exactly to this. One key question is how do you actually break down the stages? And this could be one way. Right? You really would like to remember balance the stages such that no stage wastes any time. I'm going to show you a pipeline that uses that has 5 stages: instruction fetch, instruction decode / register file read, execute or address generate, memory access, store or write back result. This is a single cycle microarchitecture that you've seen and come to love. Right? You like it so far, and you're building it now. This is the throughput that we have, assuming that you have t cycles, t picoseconds for everything. Now, this is how we divided the pipeline, basically. Instruction fetch takes 200 picoseconds. Instruction decode register file read takes 100 picoseconds. Execute takes 200 picoseconds, 200 picoseconds, 100 picoseconds. This is based on the results picoseconds that I showed you earlier, right? Remember? Well, is this a balanced pipeline? Not really, right? Not all stages. A balanced pipeline is a pipeline where all stages take the same amount of time. It's not balanced. Now, one issue you will face is that it's hard to balance a pipeline because you need to really ensure that every combinational delay, every critical path within each stage is exactly the same. Right? That may be difficult because this memory may inherently take longer than this register file, right? Now, you may want to add some more logic over here, but you may not be able to break everything nicely, right? Your design complexity may go high. It may increase. So there are a lot of trade-offs associated with how many stages actually do you put. Why not have 4 stages or 6 stages? Why not have different boundaries? And the goal here is, again, maximize throughput and minimize the critical path. But let's assume this design for now. Partly this is art, actually, also, because there are many things that you need to implement, and this is an iterative process. You may come up with a pipeline design, and you find out that your critical path in one stage is very long. What do you do in that case? Well, maybe you break that stage into 2 stages, right? That's one option. Or maybe you merge some other stages such that things are balanced. Right? So the pipeline design is an iterative process, too. OK. Well, you need to do register file writes. So somehow, I'll foreshadow some of the issues. When you're actually writing back your results, you're actually also reading from the register file. So you'd better ensure that there's no resource conflict, right? Maybe this instruction over here is reading the register that's being written by this instruction. How do you ensure that this gets the correct value? How do you ensure any instruction gets the correct value, right? Maybe when this load is being executing, this instruction needs that value. OK? And ignore for now this one. This will cause us problems. This is a control dependence, right? This is if you have a taken branch, the address needs to be fed into the PC. But when you're fetching the branch, you fetch the branch. You don't know if it's a branch, right? You haven't decoded it yet. It goes to the next stage. When you're decoding it, if you want to keep the pipeline full, you'd better know what instruction to fetch next, right? And if it's a taken branch, the next program counter, PC plus 4 in this case, is not the right place to fetch from. Right? And the branch target is determined over here, which means that until the branch is executed, you do not know which are the next 3 instructions. So how do you keep the pipeline full in the presence of branches? That's a fascinating topic. How do you handle that control dependence? What do you fetch next? So keep that in mind. OK, so let's take a look at the throughput of this pipeline. This is what you have with the values that I showed you over here with a single cycle machine. It takes 800 picoseconds to execute every instruction. Well, it could be a multi-cycle machine also, because we're ignoring the latch overhead over here. I don't show you any latch overhead. But in a pipeline machine, your instruction, your cycle time is dictated by this 200 picoseconds. The cycle time will be 200 picoseconds. And this is how the instructions will execute. Assume that all of them are independent, and these are the independent loads. This is what will happen, basically. Every cycle takes 200 picoseconds. And to be able to execute these loads, you take, this doesn't look right, 1, 2, 3, 4, 5. Yes, there you go. Because this register really ends. Yeah, you don't do any processing over here, because register file write takes 100 picoseconds. So it takes 1,000 picoseconds to execute a single instruction. Right? So basically, you increase the latency. Right? What we've done is, before, if we didn't pipeline, regardless of eliminating the latch overhead, an instruction took 800 picoseconds. Right? Now, because we pipeline, the instruction latency is 1,000 picoseconds. Because each stage needs to take the same amount of time. And we haven't balanced the stages well. Right? That's why the 5-stage, even though you have 5 stages, the speed up you get is really 4, not 5. Does that make sense? You can do that calculation yourself, because you increase the latency of each instruction now. So that's the downside of not balancing the pipeline. You may increase the raw latency of the instruction. Yes, you're improving throughput, but you're not improving throughput as much as you really could ideally. So whenever you're designing a pipeline, try not to increase the raw latency of an instruction. And balancing the pipeline is one thing you can do. The second thing is minimizing the latching overhead. Now that's a tough thing to get rid of. OK. So the second thing, well, we've discussed this. Basically, if you want to pipeline this, you'd better add some registers to latch the intermediate results, right? Otherwise, it's impossible to do something else in the data path while you're doing something in another part. So that's why you have these pipeline registers, if you will, or latches, in between the stages. That enables you to do processing in this stage independently of the processing in this stage, because this stage is using results that are latched here, and this stage is using results that are latched here, and this stage is using results that are latched here, and this stage is using results that are latched here. Make sense? And these are termed instruction fetch / instruction decode pipeline registers, instruction decode / execute ... right? That's the terminology. So let's take a look at what needs to go into these registers. Basically, whatever is needed to do the processing in this stage has to be in this latch, right? And more, because you may need processing here. You'd better propagate things that you need from the previous stages. I'll show you an example. For example, this is the fetch PC, fetch program counter. After you fetch, you get the instruction register, let's say. And you get the PC plus 4. But you don't need PC plus 4 in this stage. Why do you need PC plus 4? Because branch calculates its target in this stage, in its execute. PC plus 4 is added to some sign extended left shifted immediate. Now you form the next PC. And if the branch is taken, this next PC should be latched into the PC. So you need this PC plus 4 until here, which means that you should propagate that value across the pipeline registers. Similarly, other results also. For example, this is you read the data out from the register file for instructions that need it. You get the immediate, and you do the computation here. You latch the ALU result at the end, right? And actually, you may need this second register here, and that gets propagated down. Even though there's no processing for that register over here, it's needed to store the data to memory if the instructions are stored. Right? Basically, propagate any value that you need later on in the pipeline latches. That's one thing that latches need to contain. OK, is this clear? Makes sense, right? And obviously, no resource is used by more than one stage. Otherwise, you would get a conflict. OK, let's take a look at a quick example. But I want to make sure that everybody understands the concept now. Yes? OK. So let's take a look at loads. This is we're fetching a load instruction. At this point, you only know the PC of the load, right? And while that load instruction is being fetched, nothing is happening. Now the pipeline is empty, if you will. While this load instruction is, well, I guess load instruction does this. Let's look at the flow of a single load instruction first. Basically, it reads the registers. It generates, these are the resources it uses, basically. It reads the registers. It generates its address using the ALU. This resource is really not needed, but it has to be there for other instructions. It loads the data from memory, and then it writes back its result. Now, if we pipeline the two loads, I'll show you an example later on. Basically, they will be going through the pipeline together. But one thing, all instruction classes actually must follow the same path and timing through the pipeline stages. Which means that, for example, there may be some instruction that does not need data memory access, right? But you designed your pipeline this way such that every instruction goes through this data memory access stage. In this stage, for example, nothing else other than data memory access happens. I guess branch is communicated. Ignore that for now. But every instruction, even though they do not need this data memory access, needs to go through that stage, right? Except nothing happens for that instruction in that stage, right? You just propagate everything to the next stage. So that does have performance impact, obviously. Right? An add instruction now takes 5 cycles, 5 stages, whereas it could have taken 4 stages. Make sense? And that leads you to lose throughput also. So let's take a look at two loads. Well, I guess the load and subtract. Once the load is being fetched, nothing else happens. Now we're filling the pipeline, if you will. Once the load is being decoded, the second instruction is being fetched. Once this load is calculating its address, the second instruction is being decoded. Once this load is accessing memory, the second instruction is being executed. Nice, right? Once this load is writing back, the second subtract is accessing memory, but it's not accessing memory because it doesn't need to access memory. So it's just propagating its results. And later on, the load is gone, and subtract writes its result back. So it takes 6 clock cycles to execute. I'll ask you again, is life always this beautiful? It's not, right? In this case, I show you an example where the subtract was independent of the load. Load is writing to register 10 in MIPS terminology. Subtract is reading from register 2 and register 3. So they're completely independent of each other. But if the subtract was dependent on the load, it couldn't go and execute. You couldn't do this, right? Because assume that subtract is sourcing register 10. Load is writing to register 10. Load value is not available at this point while subtract is doing its execution, right? This is called the data dependence. And you'll have to find a way of stopping the subtract from going forward. You'll have to find a way of detecting this first. You'll need to detect whether the later instruction is dependent on a previous instruction who has not produced its result yet. And second, you need to have a build into the hardware ways of stopping this subtract from going forward until the result is ready. And that's called data dependence handling. And we'll talk about that a lot. OK, I'll go through this relatively quickly. I think you guys got the idea of pipelining, right? Basically, if you look at it from an operation view, this is what it looks like in a pipeline. Right? This is time on the x-axis, instructions on the y-axis, and each instruction going through each pipeline stage. This is the part where the pipeline is being filled, if you will. And this is where a pipeline is full. So you have 5 instructions being processed concurrently. But you're always finishing 1 instruction per cycle in the steady state. Okay? And you can also look at the resource view. At any given time, you're basically utilizing all of the stages, right, when the pipeline is full. OK, pretty pictures, but that's OK. OK, control points in a pipeline. If you've actually designed the single cycle processor, single cycle data path, the control points are the same. They don't really change, at least for the data path elements. There are some other control points that we will discuss related to stalls that need to be added. But these control points are the same. Register write signal, ALU source signal, what should the ALU do, branch condition calculation logic control signal, the PC source, mux signals. They're all the same, except they're utilized at different stages, right? Basically, how do you generate the control for a pipeline? For a given instruction, you have the same control signals, but control signals are now required at different cycles, right? Depending on the stage. There are several options for doing this. You could, for example, decode all of the control signals when you decode the instruction, right? Generate all the control signals with the same logic as single cycle data path and buffer those control signals until they're consumed. I'll show you an example of this. This is the example, basically. You could have the control logic generating all possible control signals that could be generated just based on this instruction, and classify the control signals that are going to be used later on. These are the control signals that are going to be used in the execute stage. These are the control signals that are going to be used in the memory stage, and these are the control signals that are going to be used in the write-back stage, and propagate them down as they're needed. Once the control signals in the execute stage over here are consumed, they don't need to be propagated down. So the pipeline latches can look like this if you do this. Does that make sense? You basically generate all control signals you're going to need later on. That's why now we have imbalance in the pipeline latches. Another alternative is you can carry relevant instruction words or fields such that you generate the control signals right before they're needed, right? In the stage, so if you need the control signals, the control signal, this is the memory stage. You need some control signals over here. You can generate them in this cycle such that they're available right before, instead of generating everything here and carrying it forward. That's another approach. This now equalizes the latches a little bit better. Well, which one is better? It depends. There you go. You got the answer right. It depends, right, what you're optimizing for. Yes?
Also, like for the ARM, you probably wouldn't want to do the latter one because the instructions aren't as pretty as like alpha, where it's the same field to indicate an opcode or something like that.
Exactly, yes. You may not want to do that for, if the fields are clear, you can do this more easily. Whereas because if you do this, you may be replicating some control logic also. You have some control logic here, and you may be decoding it again, right, to generate the control signals. So that's the overhead. You have some combinational overhead that is traded off with some sequential latching overhead. OK. So this is one design where pipeline control signals are generated early on. And this is the design in your book, for example. Anyway, I'm not going to go over this, but this shows signals that are, for example, a register write signal is needed in this last stage, even though the resource is present here. And that signal just gets propagated down the pipeline, and it's not used over here. OK? Although we will see that it's used for some other purpose later on when we talk about data forwarding. OK. So these were the ideal pipeline, right? Examples. So let's take a look at how instruction processing actually fares in terms of these ideal pipeline properties. And none of these are true for the instruction processing pipeline, right? You don't process identical operations in the pipeline. Different instructions do not need all stages. And however, when you design the pipeline, you need to force every instruction to go through every stage, right? That's the idea of a pipeline. And this leads to external fragmentation from the pipeline stage point of view. Basically, some pipe stages are idle for some instructions, right? An add doesn't use the memory stage, for example. And that increases latency. Sub-operations are not uniform. It's difficult to balance the different pipeline stages, and I said that earlier. And this leads to internal fragmentation, which means that from the point of view of a pipeline stage, some pipe stages are too fast. They're done quickly. But it needs to take the same amount of time because everything operates based on a clock, right? The same clock cycle. And this increases latency also. And finally, independent operations exist, but there are many operations that are dependent on each other. Instructions are not always independent of each other, right? Which means that you need to somehow detect and resolve these dependencies to ensure pipeline operates correctly. You cannot ignore these, right? And this also adds latency. All of these increase latency in the pipeline. And this also means that pipeline is not always moving, right? If you're waiting for a result, then you need to stall the pipeline. Stalling the pipeline means stopping some stages in the pipeline until the values that are needed for those stages to proceed are ready. OK? So we'll take a look at stalling a lot. And this brings me to the issues in pipeline design. Well, we still have time. Is this interesting? Yeah? Should I ask you hard questions to wake some of you up? OK. But these are actually fundamental issues in pipeline design, basically what I have described. The first is balancing work in pipeline stages. How many stages do you have, and what is done in each stage? I'm not going to talk about this further. This is more of a design problem. But you'll do this, actually, partially in your pipelining assignment, and hopefully in the extra credit even more. The second is, and this is critical, we're going to focus a lot on this, keeping the pipeline correct, moving, and full, these three properties, in the presence of events that disrupt the pipeline flow. And we've already discussed a few events. And there are three key things. One is dependencies, resource contention, and long latency operations. You could argue that long latency operations are very similar to dependencies, and that's true. But long latency operations pose difficulties in pipeline because you cannot balance things really well. So we're going to handle this later on separately. Basically, correct, moving, and full. That's what you need, right? Correct means you should get the correct result. Moving means you shouldn't deadlock. And full is good for performance, right? Assuming these two are satisfied. You can keep the pipeline full, but you're deadlocked. That way, nothing progresses, right? OK, so we'll talk about dependency handling and resource contention. And finally, the other fundamental issue is handling exception and interrupts. This is true for any machine, and I've asked you this question in the microprogram machine too. How do you actually handle exceptions and interrupts here? we've changed the von Neumann model a little bit, right? We're processing multiple instructions per cycle internally. So it better have a clean state to handle exceptions and interrupts. And more advanced, how do you improve pipeline throughput? How do we minimize the stalls? We're going to talk about this actually right now too. Okay, what are the causes of pipeline stalls? A stall is basically a stage or multiple stages in a pipeline is not moving or should not move because there's something that caused it. Resource contention is one of them, and we'll see that. Dependencies between instructions, data dependencies and control dependencies, and long latency operations. Let's look at dependencies first. I'll call it's all called dependency or dependence. Actually, I like dependence better, but I usually say dependency. Sometimes hazard is used. Hazard is very hazardous, I think. It feels kind of scary. I think it's a hazard only when it's not handled well, right? But basically, I'll stick to the term dependence or dependency. These dictate ordering requirements between instructions, right? And there are two types, data dependence and control dependence. Resource contention is sometimes called resource dependence. You really depend on a resource. But I'll treat it differently. This is not fundamental to program behavior, right? It's not fundamental to program semantics. If you have infinite resources, there is no resource contention. So we'll treat it separately. But let me first treat that actually. How do you handle resource contention? This happens when instructions in different pipeline stages need the same resource, right? Can you think of examples? Yes?
When you want to increment the PC, but you want to use the ALU to do the increment.
That's right. So that could be one thing. Exactly. Well, in that case, fetch stage needs the ALU, as well as execute stage needs the ALU, which means that you cannot fetch an instruction when there is an instruction that needs the ALU in the execute stage. So to handle that, you need to really replicate at least the incrementer in the fetch stage. Yes?
I mean, this depends on your register file, but if you're reading the operands and you're potentially writing back the result.
That's right. That's right, exactly. That depends on your register file, too. That could be if you have one read-write port to your register file, you can do only one, right? That's good. Well, solution one is eliminate the cause of contention, right? Basically, you have another adder in the fetch stage. That way, you break the resource dependence. You duplicate the resource or increase its throughput. In your case, for example, register file, you add one more port to the register file. One read port, one write port, and now you can do both in the same cycle. Well, another resource is memory, right? When you're fetching from memory, in the instruction fetch stage, every instruction needs to fetch from memory. But there's also a memory stage where load and store instructions need to fetch from memory. Let's say load needs to fetch from memory. If you have one read port to memory, again, that's a resource contention. One way of handling it would be using separate instruction and data memories, caches, as we will see. The second way of handling is using multiple ports for these memory structures, right? And the second solution, if this is not feasible or if it's too expensive, you could do this. You could detect the resource contention and stall one of the contending stages, right? Then the question is, which stage do you stall? What if you have a single read and write port for the register file, just like you described? You have a 5-stage pipeline, and this is the fetch, decode, register file read, execute, address generate, memory, and write back. You have one instruction here that's writing its result to R2, and you write one instruction here that's reading its results from R3, let's say. There is no dependencies. And you have only one port to your register file. Which stage do you stall in this case? Yes?
Well, the earlier one, because if you stall the later one, then the earlier one can't progress.
Exactly, yes. Exactly. You stall, you basically let this go such that the pipeline moves, right? Remember, our goal is to keep the pipeline moving. So you stall this one such that this can write, and now this can read in the next cycle and go. OK, I guess that was you could basically do the same thing for memory also. I hope they're not waiting for this class. OK, so that's resource contention. Make sense? You can handle it simply, hopefully, with some solution. And again, how you handle it depends on the cost of the solution as well as the performance impact. For example, it's critical to have a PC increment counter. if many of your instructions are ALU operations, you really need that ALU, right? And you know that you definitely need your program counter increment every cycle, right? So that's why program counter has its own incrementer over here. Actually, that could be a nice question, nice exam questions. If 30% of your instructions are ALU operations, and if you have one ALU where you also do the increment, what is your throughput of your pipeline, assuming everything else is ideal? You can think about it. It's easy, actually. OK, so data dependencies. Let's move on to more program-related dependencies. There are 3 types of data dependencies, and there's only one true one, which is the flow dependence. This is true data dependence. You have a read to a register or a location after a write happens to that register. Right. There's output dependence. I'll show you examples of this. This is write after write to the same register. And anti-dependence, which is write after read to the same register. You have a read register 2, and then you have a write to register 2. And you need to ensure correct semantics for all of these. But for all of them, you need to ensure semantics of the program is correct. You cannot reorder these, right, in the program. Flow dependencies, well, you need to obey all of them, but flow dependencies, you especially need to obey them because they constitute true dependence on a value, right? This is kind of not as fundamental if you think of anti and output dependencies. They're really dependent on a name. And I'll foreshadow this because we're going to fix some of these with out-of-order execution later on. But a true dependence is you're writing to, let's say, register 2, and later you're reading from register 2, right? Let's say multiply and add. It doesn't matter what you have over here. Let's assume that it's not register 2. This add needs this result, definitely, right? It's a true dependence. This is a read after write dependence. If you look at an output dependence, you have a multiply that's writing to R2, and later you have an add that's writing to R2. And you may have an add over here that's reading from R2. There's really no dependence here, right? Because this multiply is generating some results, and it happens to store its result into R2. Well, this add is generating results, and it happens to store its result into R2. And this multiply is generating a result, and it happens to store its result into R2 also. The compiler could have easily done this, perhaps, right, assuming that all of the values would be correct. If the compiler had enough registers, it wouldn't run into this output dependence problem, right?
So why does that stall the pipeline?
Well, for this pipeline, actually, it doesn't stall it. For the one I described it. But we'll see that it may cause stalls later on. We'll see that soon, actually. Does that make sense? So if 2 instructions are writing to the same register, there is a dependence on the name. You still need to guarantee that this add, the latest result, is really this add's result, right? You cannot reorder these. But it's really a dependence on a name. If you had 10,000 registers, the compiler wouldn't have used R2, right? In fact, if you have infinite number of registers, you wouldn't ever have any output dependence or anti-dependence, right? You would always store a value that's produced to a new register. That's it. Think about data flow now. Data flow never actually has this kind of dependencies, right? The only dependence in data flow processing, remember data flow from the first lecture? The only dependency, you always have values communicated between instructions. You never communicate these values between these instructions. OK, so keep this in mind. These are depends on a name, not a value, and we'll later see what we can do about them. Well, to foreshadow a little bit, in hardware, we'll try to imitate this, basically. In out-of-order execution, what we will do is we'll rename this register to a separate namespace, to a separate register file that's not visible to the compiler, such that this dependence is eliminated, such that we can execute these instructions in any order we want. Here, you cannot execute these instructions in any order you want. because they're both writing to register 2. Right? Whereas if we create another level of register file and rename register 2 to that register file and have separate registers allocated for these 2 different instructions, now I can execute them in any order you want. Make sense? OK. Yes?
But even if you rename them, don't you still need the result of the add to execute the multiply?
No. So the assumption was that these do not have. Oh, let's see. Don't you still need the result of which add?
So I don't. Whichever one comes first.
Yeah. No, you don't need the result of this one to execute this one. The assumption is that there is no true dependence between them. OK? OK. We'll get to that. That's a good question. If there's a true dependence, then you cannot do it. You have to obey the true dependencies. But we'll think about how to fix that problem also. That's the beauty of computer architecture. You can dream and try to get rid of all dependencies. Actually, I'll ask you a question soon. This is what I showed basically. This is a flow dependence, or true dependence, if you will. Read after write. This operation needs the result of this operation. Anti-dependence is this, write after read. Again, this is a name dependence. Right? So I showed you this one, write after write. It's a name dependence. The compiler, if it had enough registers, this could have been R1,000,000. Right? Again, here, this R1, the value in R1 has nothing to do with this value in R1. Right? You're just generating a new value into R1 and putting it. You could have had R1,000,000 here. Right? OK? OK. Well, this is the life is beautiful slide. What if the subtract were dependent on load word? This wouldn't have worked, right? I've already shown you this. So this brings me to data dependence handling. Let me actually stop here and take a 4-minute break. Is that good? 1:33. You guys are designing a new projector? Or?
A new laser pointer.
Laser.
Shows up on the
Because that doesn't show up on the video.
Oh, it doesn't?
Stuff.
OK.
'Cause it's not recorded.
Oh, this one doesn't show up. That's right, yes. Yeah, maybe you can design it by the end of the semester so that I can use it. You'll get extra credit. OK, we've talked about data dependencies. Oh, this went back. Now let's take a look at how we can handle them. So I'm going to give you some readings. These are actually readings for the next few lectures, Patterson and Hennessy chapter, and this relatively old now article about the microarchitecture of superscalar processors. This not only covers data dependencies, but it also talks about more advanced pipelining, interrupt and exception handling, out-of-order and superscalar execution concepts that we're going to cover later on. It's a good reference source. I thought I added one more thing over here, which is the pipeline LC3B, but apparently not. But we'll try to talk about it. So how do you handle data dependencies? With the given pipeline design that I described, anti and output dependencies are actually easier to handle. Right? Flow dependencies are more interesting, but let's take a look at why this is easier to handle. As long as you guarantee that you write to the destination in one stage and in program order, you're done, right? You can only violate an output dependence, assuming this is R2, if you reorder these instructions somehow. But in this pipeline, you never reorder instructions, right? You write to the destination register at the end of the pipeline in program order and only in one stage. So there's no problem with the write after write dependence, and there's no problem with the write after read dependence. Because you write to this register, well, write after read is this, right? You just need to guarantee that this multiply, actually we need to think about this a little bit maybe. We're going to get back to that. You just need to guarantee that this multiply reads the correct value of R2, right? So this add should not clobber the value of R2 before multiply reads the old value. So you may have a problem here.
But it would have been matched already, right? Because before the add can before the add can ever get written back, because that's the last stage.
Yes.
That value of R2 would have already been matched for the multiply.
Yes, but if oh, that's right, exactly, because this happens later, right? Exactly. So this is not a problem in this pipeline design. Yes.
unless it was out of order.
unless it's out of order. That's why we're going to handle all of this in out of order. So these are easy to handle in this simple pipeline design, because it's all in order and you write in one stage at the very end. Flow dependence are more interesting, and there are actually 5 fundamental ways of handling them. Maybe you can think of more. One is simple. You detect the dependence and wait until the value is available in the register file. Right? That's the simplest way of handling it. But you definitely need to detect it. Actually, in all of them, you need to detect it. A little bit higher performance version, you detect the dependence and wait only as much as you really, really need to wait. In other words, dependent instruction can move forward in the pipeline as long as it gets the value right before it needs it. That's the idea of forwarding the data or bypassing the data. So you don't need to wait until the value becomes available in the register file. For example, if you have an ALU operation, you only need to wait until the value can come to the input of the ALU. Right? So we're going to provide bypass or forwarding paths to enable this. We're going to look at that. This makes sense, right? Wait no longer than you really need to wait. The third option is also possible, right? You detect at the software level. These are hardware solutions. You detect and eliminate the dependence. Right? In this case, there's no need for the hardware to detect the dependence. This is called software-based interlocking. And these are more hardware-based interlocking mechanisms. Interlocking is detecting the dependence. Who does the dependence detection? Again, this is programmer versus microarchitect, right? Do you push the burden on the programmer, tell the programmer, look, this is my pipeline, deal with it? Right? You could do that. How many of you figured out what MIPS stands for, by the way? That was a question I asked a couple of...
I looked it up.
You don't remember? Is there a word interlocking somewhere there?
Yes. It's like non-interlocking.
Just without interlocking pipeline stages.
There you go. Microprocessor without interlocking pipeline stages. Initially, this was the goal of the MIPS architects. Remember, MIPS is a reduced instruction set computer. Initially, it was an extreme case. Basically, they said hardware should be simple, software should handle everything. And if you start with that philosophy, this is true, right? Later, we will see that philosophy again appearing in the VLIW, very long instruction word architectures, where it's the burden of the software to detect all of the dependencies and schedule the program such that it executes correctly in a pipeline. MIPS, initially microprocessor without interlocking pipeline stages. It's the burden of the compiler to figure this out. Right. And reorder instructions such that these dependencies do not cause a problem in the pipeline and the pipeline flows nicely. Yes, you had a question?
Sometimes you would add like no ops.
Exactly, yes, we'll see that. Basically, it may not always be possible, right? You may not have instructions that are independent. You may not always be able to reorder instructions. So in that case, what do? You add no ops into the pipeline, right? Into the instruction stream. And that reduces your performance. You keep the pipeline full, but you're keeping the pipeline full with no ops. It does increase your instruction per cycle. But this goes back to, again, your question on how the instruction per cycle is computed, right? You'd better not include no ops in there, perhaps, right? OK? In the end, it's really not the instruction. So again, this goes back to another point. In the end, your goal is really not instructions per cycle, right? Your goal is execution time, which, remember, consists of number of instructions times cycles per instruction times cycle time. In the end, you're trying to minimize that equation. OK, so this is also possible to do. And this is software-based interlocking. Well, I guess I've given you the answer. Can you do better? Predict, there you go. You saw the predict. It's actually fun, right? When an instruction is dependent on another instruction, and if you don't have the value, and you don't want to stall the pipeline, what do? And you cannot forward it for some reason, as we will see. There are cases where you cannot forward. You can predict the value, right? You have a multiply instruction. Let's say that's actually load is well, let's do multiply. Writing it to R2. And then you have a later add instruction that's reading from R2. And you don't want to stall this add. Multiply may take 10 cycles. For example, it goes into a 10-cycle pipeline. You don't want to stall this add. What do? Maybe you have some logic that says, oh, in the past, this R2 has been always 0 when I executed this add. So I'm going to assume this time that it's also going to be 0. This idea is called value prediction. But based on the past behavior of the values that were in R2, you generate a prediction. Does that make sense? Yes?
Is that really complicated to do in hardware? Because you have to like save values all the time with like previous executions.
That's right, yes. So it does, you need a table in hardware that basically, usually the way it works is, well, this actually, it's not clear if it's implemented in any processor today. But the idea is intriguing, right? You can take the program counter of an instruction and index a memory structure that gives you the past value, right? That was seen when you executed that instruction. Does that make sense? This is a memory structure that's you can search with the program counter. Okay? And it could be a big structure, of course. And this is one way of predicting. What was the past value in the previous execution of this instruction? That may not be the best predictor. Right? Maybe you find the most frequent value, and that increases your hardware complexity. Okay? Yeah. So why does this work? Or could this work? If the values are stable, it could work, right? So for example, it could work if this is a load instruction, and you're loading from an array that's all zeros, right? The values happen to be all zeros. Or the values happen to be similar. It could work. Or the values follow a pattern, right? You need to detect that pattern. Yes?
But if the values follow a pattern or all zeros or something like that, wouldn't the software designer already know that?
Not necessarily, because that's an input to the program, right? Input could be anything. It really depends. If you're doing a simulation, for example, input could be anything. Okay, so it could happen. And there are other cases where it could happen also. For example, if you have an induction variable, you have a predictable value, right? If you're doing if you have a for loop, I equals 0, I less than n, I plus equals 2, let's say, you know that you're always incrementing I by 2. So you could actually predict the entire set of i's that you're going to produce with this instruction, right? Does that make sense? So that's another example. But some other values may be very, very difficult to predict, right? If you're generating the result of a floating point computation, for example, maybe you don't do this. So you can do this selectively. So you could actually have selective value prediction. And you could actually increase hardware complexity by having confidence. Maybe you can have confidence counters. I'm confident that this past value has occurred a lot. And if you're confident, then you use this. Then you predict that this value will be 0, let's say. And then you execute the add without waiting for the result of the load to come back. That way you keep the pipeline full. But you need to do something, right? Well, something which is verify. You cannot just assume that it's correct. And that verify is important, and that actually makes the solution a little bit not so great, right? Because now you need to wait for the result of the load to be able to verify. So it takes time. Okay? So, but think about this as we're not going to cover this more, but this is an interesting solution. This is one form of speculative execution, if you will. You basically execute this instruction without actually knowing the value, right? You're kind of assuming that this is the value, and you're verifying if that's true. If you're incorrect in your prediction or guess, what do you do? Say it again. Restart. Yes, do it again. Exactly. Once, well, you need to have this value to figure out whether your prediction was correct. once you figure out your prediction is incorrect, well, you need to do something like get rid of everything in the pipeline and restart the pipeline with this instruction and execute it with the correct value now that the value is available. Right? That's called a pipeline flush. And we'll need it for other kinds of speculation also. In this case, it's a full pipeline flush. Basically, you flush all of the instructions that are after this. Right. OK. What other? There, I said 5, and I gave you 4. Yes?
You can do other things.
Do other things.
Not dependent.
You're predicting now. That's good. What are other things, for example?
Like if you're loading some value to R1, but you need to be adding R2 and R3 and then also adding R4 and R5.
I see.
You can be executing those while you're waiting for the value of R1 to be loaded.
That's right. Yes. Basically, you can do independent instructions. You can execute independent instructions. That's not what I had in mind. But you're going through the out of order execution. Right. So you could do that. This is essentially doing that, right?
Yes, but at the hardware level.
At the hardware level. That's right. Yeah, I guess I could have added it at the hardware level over here. You're right. You could do that. I thought you were going to say something else with the other things, though. So we'll see that. We'll see exactly what you say when we talk about out of order execution. Yes.
If what you're predicting is just a yes/no, then you can take both paths
Uh-huh.
and then choose one later.
That's right, for a dependence. That's true. That's a tough thing to do with values. But yes, with control, with branches, we will see that.
Yeah,
You're
so,
right.
but with any kind of conditional execution, because branches aren't the only thing that are conditional. Like especially in ARM, like everything can be conditional. So you could
That's
just
true.
execute all of them and then roll back.
Pick the one that's the correct one. That's right, exactly. That's called multipath execution. And it's mainly used for branches because, well, in ARM, the difficulty over there, we will get to it, is soon your paths will explode. It's because if everything is conditional, it's exponential, right? You have 2 to the n paths and only one of them is correct. But yes, that's actually a viable option, especially if you do it selectively, and we'll cover that. That's good. I was thinking of something else. Do something else. That's exactly. That's similar to what you said, except I was thinking of do totally something else. Meaning, don't execute this particular thread. Execute some other thread, some other program. Right? While your virus checker is seeing a stall, execute something from your email thread. Right? This idea is called fine-grained multi-threading. Basically, every cycle you fetch from a different thread, such that there's no need, absolutely no need to detect data dependencies or control dependencies within a single thread. So you keep the pipeline full, and every stage has an instruction from a different thread. Yes?
How does the hardware know? I thought that's like an OS just giving the hardware a stream of instructions. Like that's at the OS level, isn't it?
Well, the hardware actually has multiple contexts in this case. The hardware keeps track of multiple threads. So you have multiple program counters, multiple register files, and every cycle you fetch from a different one.
And that's
And-
why, sorry, on a lot of Intel processors, like even if you have 4 cores, it'll actually show up to the operating system as though you have 8, because the operating system actually gives 2 threads to each core.
That's right. Except Intel processors are not fine-grained multi-threaded. They use a different form of multi-threading, which we will talk about. They're more simultaneous multi-threading. So they cannot switch between threads. They actually can execute from threads in the same cycle at the same time.
Is that hyper-threading?
Well, that's Intel's term for simultaneous multi-threading. Yes, hyper-threading. It's hyper-marketing, I guess. That's yeah. But yes, do something else. This is fine-grained multi-threading. Basically, this is what your hardware looks like. Let's say we have this 5-stage pipeline. 1, 2, 3, I guess 1, 2, 3, 4, 5. There you go. That's better. This is the fetch stage. Now your fetch stage has 5 program counters. And you have a mux selecting what to fetch from. And this goes into your instruction memory. And you basically switch between the program counters every cycle such that no stage there are no two instructions in the pipeline from the same thread. Each thread has at most one instruction in the pipeline. Right? That way, there's no need to detect data dependence, right? Because you fetch from this thread only after its instruction is completed. And then you fetch from this thread only after its instruction is completed. Yes?
I feel like this would make it extremely difficult to predict what's going to happen with your execution. And like if you're doing I/O, in which order things will happen, if you're just constantly randomly switching between different threads.
Why would it make it unpredictable? You
Unless you're just going straight through 1, 2, 3, 4, 5, 1, 2, 3, 4,
That's right.
5.
Yeah, exactly. That's
Say
the.
you have two different programs that are both doing I/O. I feel like they would interfere with each other at a later point because you just keep on skipping between their operations, so they could go in either order.
Yeah, you're interleaving their operations, right? If there's any dependency between the programs, then that'll get resolved. Think about it. Yeah. Yes.
What's as far as like when it first starts up, like is it just gonna run one thing and then it's like inserting no ops, or is it switching between all those like defaulting to no ops? Because I'm saying like
I see.
You know, when you start up, you have to only have like one.
I see.
thread.
What if you don't have many threads? Yes, that's the downside of this approach, right? The downside is if you do not have enough threads to execute, you fetch no ops into the pipeline. In the extreme form of this multi-threading. This is fine-grained multi-threading. And that's in fine-grained multi-threading, you ensure that there are no two instructions from the same thread in the pipeline, at least such that you need to resolve dependencies. Right. So basically, if this PC doesn't have a valid thread, well, bring an op. Okay? Yes?
So you would have a different reg file for every.
Absolutely, yes. So now you're getting into the hardware cost of it. So if you have this is the register file stage, well, you have 5 different register files, right? And you have a mux, right? That's the hardware cost. Make sense? You need to replicate basically the thread context. And of course, the OS needs to be aware of this because now the OS can put 5 different threads over here. But this is a very powerful design. There's no need for branch control dependence handling. The problem goes away, right? You don't need to know which instruction to fetch next because you have another thread to fetch from. And you know that's totally independent. Yes?
Wouldn't this like make caching really difficult because you're kind of violating temporal locality? Because you have these 5 different threads running. They're all going to have, they're going to be filling the cache with random things. They don't really have that temporal locality.
Yeah. Well, for each thread, you may still have temporal locality, but now you're getting into a good point, which is your cache is contended by 5 different things. So the same amount of cache space may not be enough. Right? You may need to increase your cache space to actually keep your hit rate. But you're right. As long as you keep adding more threads, you have more contention over here. These are all very good points. So there are potential downsides. But this is one way of eliminating any kind of dependence, actually. You don't need to do any kind of detection at any level. The downsides you've already talked about. And many of these people have looked at all of these downsides over the years. And maybe you can find better solutions also. Okay? We'll get back to this. This is actually a lot of the existing GPUs use fine-grained multi-threading. They multi-thread across different threads. Every cycle they fetch from a different set of threads. Why? Because it's simple. They don't need to have the detection logic for flow dependencies. Okay. Okay, I can move on now. So let's go back to some of these concepts before we talk more about these later on. So interlocking, I already told you that this is the detection of dependence between instructions in the pipeline processor to guarantee correct execution. And we talked about software versus hardware-based interlocking. So I'll go through this quickly. And I guess we've talked about the MIPS acronym. So you now know what it stands for. So how do you actually detect? Let me go into the hardware details a little bit, but I'll try to go quickly. How do you actually detect this dependence? One approach is scoreboarding. This is the simplest approach. The idea is each register in the register file has a valid bit associated with it. And an instruction that's writing to the register file resets the valid bit when it's decoded, saying that, oh, I'm going to write to this register. So know that if you want to read this register, the value in the register file is not correct. And when an instruction gets to the decode stage, it checks if all of its source and destination register are valid. If the answer is yes, there's no need to stall, right? You can just keep going. There's no dependence. Otherwise, you stall the instruction. Stall meaning stall the stage such that the instruction doesn't move, but all instructions over there move. Make sense? So the advantage of this is simple. This is 1 bit per register, right? The disadvantage is, well, you need to stall for all types of dependencies, not only flow dependencies. That's true, right? Based on what I described. Why is that? Well, you can fix this problem a little bit. Yeah.
Well, you can look at the opcode, right? So that, and see where the register is. So if you examine the whole operation more closely, you can see whether it's a destination or source.
Yes.
And then based on that.
But even if it's a destination, you need to stall. So let's say I need to draw a scoreboard here. Let me get rid of this multi-threaded engine. You have this register file, and you have one valid bit associated with each register. And let's say this is the destination, R1. It's not valid. And you're decoding an instruction whose destination is R1.
Oh, I see.
Right? You still need to stall, right? Make sense? Why? The advantage is exactly the disadvantage, right? Because you have only 1 bit. I didn't tell you when this valid bit gets reset, but logically it would get set to 1 when the instruction writes to the register file, right? Now, if you do not stall on a write after write dependence, let's say, basically you have an instruction writing to register 1 over here, and now you're decoding an instruction that's also writing to register 1. Let's keep this cooked up right now for now. You could argue that why are you writing to register R1 if you're writing to register R1 again? Well, I'll give you a reason, side effects. Right? Maybe this instruction is a side effect, which also sets the condition codes, whereas this instruction doesn't have a side effect, and then you're later using the condition codes. So there's actually a good reason to potentially do this, right? I've always been thinking about that reason, and it came to me right now. Side effects, why not? You can do anything that looks stupid as long as you have something else that's also happening in the instruction, right? That's why people don't like side effects, because you would think that this is only writing to R1, but maybe it's also setting the condition codes, right? Okay, so this could happen. But in this case, if you do not stall this instruction, what happens is both of them will go R1, R1. They're both writing. This one's writing to R1, and this one's writing to R1. And when this one writes into R1, it'll set the valid bit. Whereas that's not true, right? There's someone else writing to R1 over here. So the next instruction that comes that sources R1 should not get this value. It should really get the value from here. That's exactly the reason you need to stall for all types of dependencies, because you have only 1 bit per register. So how would you fix this problem? It's a simple fix. Yes?
Add a few more bits.
Add a few more bits. That's right.
So the number of pipeline stages you have, and then 1 bit in a key.
That's right.
At that stage, fix that register file.
That's right. So I think you're telling me about a counter, right? Add a counter, right? How many registers, how many instructions are there in the pipeline that are writing to this register, right? Keep counting. So if you have actually 2 instructions writing, 2, this is your count of writers. And when this one writes, it decrements the count to 1. And if the count is greater than 0, this instruction over here stalls. Only for flow dependencies. Yes?
So you said the count is incremented at the beginning, and it's decremented at the end, right? Why can't you simply just have like an OR?
You could do that too. Yes, that's right.
Solve them and then have 1 bit.
That's right. That's another possibility. You could do an OR also. I think that may be what you were suggesting too. Basically, you need to ensure that an instruction that needs this register does not go forward. And for that, you need more than a bit, assuming you're not stalling on write after read and write after write dependencies. OK? There are other ways of implementing this. OK. That makes sense? There we go. You have a burning question? Or
We can talk about it.
okay, we'll talk about it later. But basically, that's how you can fix, that way you can enable write after writes to go into the pipeline. You can have multiple instructions writing to the same register. And that's why these are not true dependencies, right? You can eliminate them somehow this way. But you just need to ensure that they're obeyed still. Okay. How do you actually do the dependence detection? There is also another way of doing this, and you can have a combinational dependence check logic. You don't need to have the scoreboard. Again, you can always, almost always, you can translate the sequential logic to combinational.
That's what I was saying.
Oh, that's what you were saying? Okay, I see. Yeah, there you go. Basically, special logic that checks if any instruction in the later stages is supposed to write to any source register of the instruction that's being decoded. You basically know that there is this, let's say you have two sources, source 1, RS2, and you have an instruction that writes to destination over here from this stage. And you have another instruction that writes to destination from this stage. Let's call it the execute, mem, and RD is our destination, and write back. Basically, you compare all of these, right? Is it equal? 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 And if there's any equality, you stall this instruction, right? That's another way. Well, yeah. If yes, then stall the instruction pipeline. If not, no need to stall, no flow dependence. In this case, there's no need to stall on anti and output dependencies, right? Because you're really checking for flow dependencies. You detect the flow dependence really easily. Obviously, the logic is a little bit more complex than a scoreboard in this case, right? And logic becomes actually more complex as we make the pipeline deeper, right? As you make the pipeline deeper, 50 stages, how many comparators do you have? Well, a lot, right? And all these wires need to be routed to do this comparison at this particular stage, right? Okay, and we'll see this actually. We'll do, well, flash forward, think superscalar execution also. You can make the pipeline deeper and wider. Wider meaning you can have multiple instructions per cycle or multiple pipelines. Now you need to detect dependencies across the depth as well as width. And that's a lot of logic. If you look at one of the exam questions from, it wasn't last year, it was the previous year, we gave the students logic and asked them, what does this logic do? And that was the dependency check logic. So you can take a look at that for superscalar execution. But this could be a disadvantage. Scoreboarding may be more viable sometimes. Okay, so once you detect the dependence somehow in hardware, what do you do afterwards? Well, the observation is that dependence between two instructions is detected before the communicated data value becomes available. You can stall the dependent instruction right away, right? If you know this. You can stall the dependent instruction only when necessary, data forwarding and bypassing. I've talked about this, and maybe other things. Let's look at these cases first. Well, this is kind of obvious, right? Stalling the dependent instruction right away. How do you implement this? Well, you insert no ops into the next stage, right? That's one way of implementing this. This instruction cannot move, but this instruction over here is moving. What should come here in the next cycle? Well, a no-op, right? And we'll see how that's implemented. You could either set the control signal such that no harm is done in the next stage. Basically, you insert a bubble into the pipeline or a no-op into the pipeline. Or you could have a valid bit for each pipeline register saying this instruction is valid or not valid. And if the valid bit is 0, this means that ignore what's happening in the pipeline registers. Don't do anything that would affect any state. That essentially makes this instruction a no-op over here. That's an implementation. Okay, so data forwarding and bypassing. Basically, if you have a consumer instruction, it has to wait in the decode stage until the producer instruction writes its value in the register file, right? That's the problem if you do just stalling. But we do not want to stall the pipeline unnecessarily. And the observation I've already told you, right? The data value needed by the consumer instruction can be supplied directly from a later stage in the pipeline instead of from the register file, right? Basically, whenever the value is available, supply it. and don't make the dependent instructions stall unnecessarily. That's the idea. And how do you implement this? Basically, you can add additional data dependence check logic and data forwarding paths or buses to supply the producer's value to the consumer right after the value is available. Right? Instead of using this path from the write back into the register file, well, this is the ALU, right? Imagine the ALU over here. You supply a path such that ALU's result goes back directly into the stage. Or you'd supply another path from memory such that memory's result goes back directly into the input of ALU. Does that make sense? So whenever the value is available, supply it to a previous instruction in the pipeline. You need additional checking logic and additional buses to support this. And I'll give you some examples of this logic. So the benefit obviously is now the consumer can move in the pipeline until the point the value can be supplied, less stalling. Right? I guess before we go into some of them, there's a special case of data dependence. Actually, control dependence is a special case of data dependence, right? It's really a dependence on the instruction pointer or program counter. Program counter is a register. And every instruction is dependent on the previous instruction based on this, right? In a sequential von Neumann machine. So you can think of control dependence as a special case of data dependence. But we're going to treat it separately because this dependence is critical for the flow of the pipeline because you have a lot of branches. The key question over here is what should the fetch PC be in the next cycle? Well, answer is simple, right? The address of the next instruction that should be executed. Well, what should that be? All instructions are control dependent on the previous ones. Well, this is kind of obvious in a von Neumann machine, right? Because you know that the definition of each instruction is increment the PC. That's the semantics for each instruction. If the fetch instruction is a non-control flow instruction, next fetch PC is the address of the next sequential instruction. So this is nice. This is really easy to predict probably, right? If the instruction you're fetching is an add, then you know that in the next cycle the program counter should be program counter plus the size of the add instruction. And this is where the variable size ISA makes life harder. We'll get back to this actually. This is to determine if we know the size of the fetched instruction. Otherwise, you need to wait until decode, right, to figure out the next fetch PC. Does that make sense? Is everybody following? Because when you fetch this instruction, this is the fetch stage. You have the instruction memory or instruction cache, and you have the program counter. Let's say you fetch this instruction. Instruction moves to this stage. This is the decode stage. In the next cycle, while this instruction is being decoded, you'd better be fetching from the next program counter. So you should have some logic that says PC plus X. Let's say plus 4. That goes into the PC. Now, if you do not know the size of the instruction, this doesn't work, right? If you do not know the size of the instruction, you need to wait until the size is figured out, which doesn't happen until the end of decode. Which means that you cannot fetch the next instruction while this instruction is being decoded. So that's where a variable size ISA complicates pipelining, right? Variable length instruction ISA complicates pipelining. Does that make sense? Okay. If the instruction that's fetched is a control flow instruction, then your life is a little bit harder. How do you determine the next fetch PC? And we're going to answer that question. We're going to have a lecture. I don't think we're going to finish data dependence handling, but we're going to start that lecture in the next lecture, where we talk about how do you determine the next fetch PC. But there's also one question, right? I kind of had this branch here, if you will. How do you know whether the instruction that you fetched is a control flow or a non-control flow instruction? And the answer is, at this point, you don't. Right? You're fetching some instruction at some PC, and you have no idea what it is, because you haven't fetched it yet. But you do need to know whether it's a branch or whether it's a non-control flow instruction to determine the PC appropriately. Right? Yes?
Are there some implementations that do some light decoding on the fetch?
Yes, so that's one.
Like some very light logic to look at the opcode.
Uh-huh. That's right. If you could do that, if you have enough time in this path, then you could potentially do that. That's a good point, basically. Some implementations actually have, this is called pre-decode, or pre-decoded iCache. And I'm going ahead a little bit, but basically for each instruction in the instruction cache, they have a bit saying, is this a branch, is this a branch, is this a branch, is this a branch? And you update it after you see the instruction stream once, after you decode it. And then you can check that bit and use that bit to either increment the PC by 4 or predict the next fetch PC somehow, if you want to do that. But we'll get back to that. Okay? Okay, this is fun, right? How do you keep the pipeline full? This is a very fundamental form of data dependence. Okay, let's see if we want to continue. I think I'll stop here. This is a good place to stop. And we'll continue, is it Friday? Yes, Friday, with more data dependence handling.